each motor has a reading for how much current is running. There's current transformers. A ground fault circuit interrupter, a GFI receptacle that trips if there's 5 milliamps going where it's not supposed to. It internally in that rectangular receptacle has a test and reset button on it. You've got 120 volt circuit, you've got line 1 and neutral, and then the ground, the bonding conductor. So in normal conditions, you've got a load here, and you've got 2 amps going on that line conductor. The neutral is going to have 2 amps going on. Because that neutral is where you go, that's exactly what that, whatever it is, draws. If for some reason there was a breakdown in insulation, or moisture gets in there, and somehow part of that current ends up going on that ground or bonding conductor, or if you're hanging on to a metal, anything part of that equipment, and some kind of breakdown in here allows current to flow looking for a ground over here. If there is 0.6 milliamps is what that ground fault interrupter will trip at. And how does it see the difference between here and here? Current transformer. This current transformer seeing how much current is going there. Current transformer on that conductor seeing how much current is going there. And the circuitry inside there is comparing those, seeing if it's set a tolerance 4 to 6 milliamps, then it's going to open the circuit. Okay, now it's auto transformers. An auto transformer has a part of its winding common to both primary and secondary. With the isolation transformer, they were physically, electrically not connected. But with the auto transformer, the transformation ratios are calculated in a similar way to the normal 2-winding or double-wound transformer. When an auto transformer is used to step up the voltage, part of the winding acts as the primary, and the entire winding acts as the secondary. When the auto transformer is used to step down the voltage, the entire winding acts as the primary, and part of the winding acts as the secondary. The action of the auto transformer is similar to the 2-winding transformer, however, is transferred from the primary to the secondary winding by the change in magnetic field. The amount of the step up or down depends on the turns ratio of the primary and secondary coils. Each coil is considered separate, although some of the turns of the coil are common to both the primary and secondary. So when the voltage is stepped up, part of the winding is the primary and the entire secondary is the secondary. So this is your voltage applied to it, that's your primary. So you're stepping up the voltage so that this many turns is used for the primary, all of those turns are used for the secondary. And if it's a step down transformer, your applied voltage is connected to all of those turns, and the secondary is connected to a smaller number, giving you a lower voltage. Auto transformers lead to savings in copper, but they are limited to small ratios of transformation. This is because an open circuit occurring in part of the winding common to both primary and secondary can cause a large primary voltage to be impressed across a lower voltage secondary load. A double wound transformer can also be connected as an auto transformer. You see this a little easier to understand. transformers are transformers that contain only one winding. The word auto means self, and autobiography, for instance, is a book that someone writes about his or herself. The single winding of the auto transformer is both the primary and the secondary. The primary winding is part of the winding connected to the source. So in this case, the source is connected 240 turns. The secondary winding is part of the winding connected to the output or the load from A to B. In this example, the primary winding is connected across 240 turns of wire, and the output is connected between terminals A and B. The output contains 200 turns of wire. Different methods can be employed to determine the output voltage. One method is to use the transformer formulas. So you calculate the voltage over here by using all these formulas and end up with 100 volts. Another method of determining voltage with the number of turns known as is by the volts per turn. The primary windings always determine the volts per turn of the auto transformer. In this example, the primary contains 240 turns of wire and has an applied voltage of 120 volts. So to determine the volts per turn of the transformer, divide the volts by the number of turns, and you end up with 0.5 volts per turn of wire. So in this example, the secondary portion of the winding contains 200 turns. Since the volts per turn of this transformer is 0.5, the secondary voltage can be determined by multiplying the number of secondary turns by the volts per turn, and again you get 100 volts. Auto transformers can contain multiple taps. In this example, there are 65 turns of wire between terminals A and B, 120 turns between terminals B and C, 160 between C and D, and 45 between B and E. The first step to determine the voltage produced between each tap is to determine the volts per turn of the transformer. The primary or input is located between taps B and E. This winding contains a total of 325 turns. So you add 120, 160, and 45. So we get 208 volts, 325 turns, so the volts per turn is 0.64. The output voltage across terminals A and B can be determined by multiplying the number of turns by the volts per turn of the transformer. And if you took a voltmeter, you'd see 41.6 volts between A and B. And the calculation would tell you 41.6 volts also. The voltage between any terminals can be determined the same way. Between B and C, there's 120 turns of wire, 120 times 0.64, 76.8 volts between B and C. Between A and E, there's 390 turns. So the voltage between terminals A and E will be 390 volts. Or 249.6. 390 turns divided by 0.64, 249.6 volts. Some auto transformers contain a sliding tap that permits the turns ratio to be changed over the full range of the transformer. These transformers are called variable transformers. There's a couple in the left that we can look at. In the example, the voltage to the load can be adjusted for any value between 0 and 120 volts. The primary is 120 volts here, so you can change the number of turns between 0 and 120. Common brand names for these transformers are PowerStat and Variac. Variable transformers are often designed to permit a step up in voltage. In this example, the transformer can provide an output voltage of 0 to 120 140 volts instead of 120. So your primary is 120 volts, but there's an extra 20 volts available if you go past there. This transformer is a variable transformer. To connect the transformer to operate between 0 and 120, connect the power to terminals 2 and 4. I get all those on there. Anyway, and so you have access to different voltages on here. There's no diagram here showing you where to connect to and what volts are available. An auto transformer is employed to reduce 480 volts to 240 volts to operate a load. The load has a current of 4 amps. Each of the primary lines supplying power to the transformer will have a current flow of 2 amps. One of the common rules to apply to transformers is power in equals must equal power out. So auto transformers offer some advantages over isolation type transformers and also have some disadvantages. Advantages: auto transformers are generally less expensive than isolation type transformers because they contain only one line. Auto transformers generally exhibit very high efficiencies in the range of 98% to 99%, and auto transformers can provide variable voltages. The main disadvantage of an auto transformer is that it does not provide line isolation from the power source. Isolation type transformers are often used because of their ability to reduce voltage spikes and electrical noise that occur in the power source. Since there's no separation between the load and the power source, auto transformers will transmit spikes of electrical noise to the load. And a little bit on power transmission. Although a transformer is a simple device, it makes it possible to transmit large amounts of power over large distances with minimal losses. In power transmission lines, the power delivered is the line voltage times the current. Therefore, a large voltage current is smaller. For example, to transmit 200 kilowatts over 100 miles with a line voltage of 1,000 volts and amperage, 200 amps would require a large diameter conductor. If the voltage were raised to 14,400 volts, you'd end up, instead of 200 amps, you'd have 13.8 amps, and a much smaller conductor could now be used. The conductor size can now be reduced while still running the acceptable power losses. The cost of the transmission line will be much lower. The power loss to the conductor is calculated P equals I squared R. For the 13.8 amp conductor, the power loss is 0.0048 times the power loss for a 200 amp conductor. This means that the conductor size can be reduced and still operate with acceptable power losses. So here it shows a simple transmission system. There are applications for transformers at both ends of the system. The voltage is increased or stepped up to 69 kV for transmission, and then stepped down to 480 volts for distribution. So you're generating it at 460 or 4160, transforming it up to 69 kV, and then when you get as far as you need to get to your end user, you can transform it back down from 69,000 volts to 480 volts. There's one more type of transformer that you may run into, may see in control panels. Transformers often contain more than one winding. One good example of this is a common control transformer used to change 240 or 480 volts to 120 volts to operate motor control circuits. So the primary of this transformer is here, where you can have the option of connecting either 240 or 480 volts here, wherever you have best access to, and the secondary is here, where you'll have 120 volts. That's a little fuse holder there that you can put a little glass cartridge fuse in. This type of transformer contains two high voltage windings rated at 240 volts each, and one lower voltage winding rated at 120 volts. So one winding H1 to H2, 240 volts. The other winding H3 to H4, 240 volts. And the ends are out here. Each one's a separate connection terminal. And your secondary 120 volts X1 and X2. The two windings rated at 240 volts are generally used as the primary. This transformer is intended to change either 240 volts or 480 volts to 120 volts needed to operate motor control devices. One of the high voltage windings is labeled H1 and H2. The other high voltage winding is labeled H3 and H4. The low voltage winding is labeled X1 and X2. Any transformer you're going to see, the high voltage, the primary, is going to be labeled H, the secondary is going to be labeled with an X. Notice that the two of the high voltage leads have been crossed. This is done to determine or to permit the two high voltage windings to be field connected either in series or parallel. So they're not physically connected, they're just crossed so the connection points are more easily, you can use jumpers across here to use either 240 or 480 volts. Each high voltage winding contains twice as many turns of wire as the low voltage winding. Turns ratio 240, 120, twice as many turns. This produces a turns ratio of 2 to 1 between each of the high voltage windings and the low voltage winding. If the transformer is to be connected for high voltage, a jumper or link connects terminals H2 and H3 together. This effectively connects the two high voltage windings in series. If 480 volts is applied to terminals H1 and H4, each high voltage winding will have a voltage drop of 240 volts. Connecting the high voltage windings in series effectively adds the number of turns in each winding, producing a turns ratio of 4 to 1. 480 volts divided by 4 gives you 120 volts. So you're in series, so you're adding turns, more turns, higher voltage. If the transformer is to be connected for low voltage operation, links or jumpers are used to connect terminals H1 and H3 and H2 and H4 together. This effectively connects the two high voltage windings in parallel with each other. In this type of connection, the turns do not add, and the transformer has a turns ratio of 2 to 1. If 240 volts is connected to the terminals H1 and H4, the low voltage windings will produce 120 volts. Another type of control transformer employs a single high voltage winding that has been tapped at specific points instead of separate windings. The tap labeled 0 is the common tap. If 208 volts is connected between terminals 0 and A, 120 volts will be produced between terminals X1 and X2. If 240 volts is connected between 0 and B, or O and B, then you'll have 120 volts, again produced at X1 and X2. The points at which voltage is applied to the high voltage winding determines the turns ratio between high and low voltage windings. So it gives you can stop one transformer for multiple voltage, primary voltages. Another very common type of multi-tap transformer is a distribution transformer that supplies power for many homes and businesses. This transformer contains one high voltage winding used as a primary and a tap secondary winding. Primary voltages vary from one area to another and one power plant to another. Primary voltages of 7.2 kV, 12.47 kV, and 13.8 kV are common. The secondary produces a voltage of 240 volts at the center tap. The 240 volt secondary tap is connected to an overcurrent protective device such as a 2-pole circuit breaker or fuses. The transformer center tap is connected to the neutral bus bar and the neutral conductor. The neutral conductor is grounded to earth. A voltmeter would indicate voltage 240 volts between the two secondary terminals from here to here, and 120 volts between either one of these two connected to neutral. And you can do a whole bunch of calculations for all the taps of the multi-tap transformer too, but we don't have to get into it. What you'd end up with, we're just going through what would happen here. Several methods can be employed to determine the values of transformers that contain multiple windings. In this example, the transformer contains a single primary winding with a connected voltage of 240 volts and 800 turns of wire. There are 3 separate secondary windings with voltages of 360, 120, and 48 volts. To determine the values, treat the primary and each secondary as a separate single transformer. And if you go from here to here, do similar calculations as before. Turns ratio from here to here is 1.15. So with that turns ratio, you calculate the current here first using 360 volts and 720 ohms. Get the current. And with the turns ratio, you can calculate from here to here. The primary current for this part is 0.75 amps. And all the way through, and this will be on Blackboard too, if you want to go through all the calculations, you end up doing calculations for each one separately with the primary. You end up with the secondary current for this, or primary current for this part of it is 2 amps. And then a primary current for the third part is 0.8 amps. So the primary current for that transformer, if all 3 of those secondaries are used, you can have a primary current of 3.55. Or you can use the volt amps. Power in equals power out. .55, 3.55. No matter how you do the calculation, your primary current are still the same. And that's all there is for transformers.
How many more weeks left?